Let's talk about friction. They are somewhere around. Let's talk about friction. Where are they? Where did I leave the extras, you guys? No, I had. Oh, here they are. Here you go, Hannah. All right. So friction. Even when a single force is applied to an object, it is usually not the only force affecting the motion. This is because of friction. Friction is a force that always acts in a direction to oppose motion. We've seen that already. It's due in large part to irregularities in the two surfaces that are in contact. Even very smooth surfaces are bumpy when viewed with a microscope. When an object slides against one another, it must either rise over the irregular bumps or else scrape them off, and either way requires a force, and that would be the friction force, right? The force of friction between two surfaces depends on the kinds of materials and how much they are pressed together. Rubber to concrete? Let's just change that. Rubber concrete. That should be rubber on concrete, shouldn't it? What does your page say? I don't know. I don't know how you can make rubber concrete. Rubber against concrete, for example, produces more friction than steel against steel. That's why concrete road dividers are replacing steel rails. Now, you don't see these kind of rails anymore. Those of you that live out in the country, you might see those over sort of old bridges. Anybody, do you know where there's one like that, Riley? Through the park? Yeah, do they still have those steel ones? Really? Oh yeah, I think you're right. You're right. Yeah, I wonder why they have those. But these are sort of the old 60s, 70s style. They've been replaced with this kind of thing. Think about when you go to around Portage there, and there's that sort of, the bridge kind of thing, and there's the divided. You see them like this. Why are they concrete, and why are they that shape? Well, if you look carefully, they're wide at the bottom so that when the car gets up to them, it's rubber on concrete instead of car, steel, or plastic up against steel. Okay, so it's actually to slow you down if you run into it. Not really sure what Joey's doing back there. What's he doing, Peyton? Is he? Interesting. So notice that the concrete divider is wider at the bottom. So the tire of a sideswiping car rather than the steel body makes contact with greater friction between the rubber tire and the concrete is more effective in slowing the car down than the contact between the steel body of the car with the steel rail of the other design. The other thing that they do at those kind of bridges, have you ever seen the big plastic drums there? Right where sort of the divide happens? Do you know what's in those? Or probably not water here in Canada. Probably sand, and they're probably half full. Right? So that when you do hit them, there's it sort of can dissipate the energy, right? They're obviously not going to be like full of concrete. That make a lot of sense. When there is friction, an object may move at a constant velocity while a force is applied to it. In this case, did I miss part? No. In this case, the friction force just balances the applied force. The net force is 0. Did I miss part, Clayton? Oh, really? Oh, there is. I never knew that. Well, I got to fix that, don't I? Okay, well, I'll just ignore that, and I'll just read from the page. Thank you, Peyton. I'll have to... Yeah, okay, so I'm reading from the page then now, right? So it should say, friction is not restricted to solids sliding over one another. Friction occurs also in liquids and gases, which are called fluids, those which flow. Fluid friction occurs when an object moving through a fluid pushes aside some of the fluid. Have you ever tried running a 100-meter dash through waist-deep water? Probably not, but you may have been in the pool and tried to run around. It's hard to do, right? It's actually pretty good exercise. So it's high resistance, but low impact. The friction of liquids is appreciable even at slow speeds. Air resistance, the friction that acts on something moving through air, is a very common case of fluid friction. You don't notice it when walking or jogging, but you'll notice it for higher speeds as in skiing, downhill, or skydiving. Now, you've probably all done this. Driven down Main Street and put your hand out the window, right? And you can put your hand out the window like this, no problem, right? But when you get up to highway speed, you put your hand out the window like this, and what happens? Your arm goes back and it hurts your shoulder. Yeah. Why is that? Air resistance. And then this is a lot of fun too, right? Yeah, it's a lot of fun, yeah. Okay, right? Low air resistance, exactly. So the faster you go, the greater the air resistance. The faster you go, the greater the air resistance. When there is friction, an object may move at constant velocity while a force applied to it. In this case, the friction force just balances the applied force. The net force is 0, so there is no acceleration. For example, in figure 4.9, the crate will move at constant velocity when it's pushed just hard enough to balance the friction. The sac will fall at a constant velocity when the air resistance balances its weight. And what is that constant velocity referred to as? Terminal velocity. It is the fastest that you can go due to air resistance. There's a question on the side there in sort of a black box. How do I have it in clicker format? I do. I don't know. Is it worth getting the clickers out for 3 questions? Yeah? Okay, well, go get the clickers then. All right, so figure 4.6 shows only 2 forces acting on the book. Its weight and the support force from the table. Doesn't the force of friction act as well? Yes or no? Y or N on your clicker. I think I have to go on to the next question then and give you the answers at the end. Only one question? Okay, good. Oh, the correct answer is no. Why is there no friction? Well, the forces are balanced. There's no attempt at motion. There is no motion. The answer is no. Let's see what the fine print says. The answer says no, not unless the book tends to slide or actually does slide across the table. For example, if it's pushed toward the left by another force, then friction between the book and the table will act toward the right. Friction forces occur only when an object tends to slide or is slide. So there has to be a tendency for motion or there has to be actual motion. If it was on an inclined plane, then absolutely, friction. Okay, so suppose a high-flying jumbo jet cruises at a constant velocity when the thrust of its engines is a constant 80,000. What's an MN, do you think? No. Meganewtons. Yes. If I was a wrestler, I would be known as Meganewton. No? Yeah? So, constant thrust of 80,000 meganewtons. What is the acceleration of the jet? Oh, sorry. I encourage you to read carefully. Yes, correct answer is B. What does constant velocity mean? No acceleration. Is that a celebration, Hannah, that you got it right? Good for you. The acceleration is 0 because the velocity is constant, which means not changing. Very good. Okay. What is the force of air resistance on the jet in the previous question? The one about the jumbo jet and the 80,000 meganewtons. Is it 80,000? I guess that would be... I better not put units in there, right? You worry when you're worried it's a trick question, aren't you? Go with the common sense one, right? Don't overthink it. Remember that it said that it was cruising at a constant velocity and the thrust of its engines is a constant 80,000 meganewtons. So what is the answer? Someone, who will be last? Correct answer? Yes. Constant velocity. Right? If there's 80,000 meganewtons of applied force, if it's a constant velocity, the air resistance is going to have to be exactly the same. Let's see what the fine print says. Since the acceleration is 0, it follows from A equals F over M that the net force must be 0 This implies that the force of air resistance must just equal the thrusting force of 80,000 meganewtons, but must be in the opposite direction. So the air resistance is 80,000 meganewtons. All right. You can put a book on a table, and no matter how you place it on its back, upright, or even balancing on a single corner, the force of the book on the table is the same. Allow me to demonstrate. To grab a textbook here, right? So I take a big, heavy textbook here, right? Does it matter? Does it matter whether I put the book flat, like we normally put books, or if I put it on its spine, like that, or if I balance it on a point, like that? Does the weight of the book change? No. Does the normal force in the book change? No. Therefore, the friction force is exactly the same. Most people think there's more friction here than there's here. They're wrong. Okay? Because the weight of the book is exactly the same, which means the normal force is exactly the same. As long as this back of the book is the same material as the spine, right? Like if this was sandpaper and this was like Teflon, obviously it would be different, right? Okay, so this can be checked by doing this on a bathroom scale, where you'll read the same weight in all cases. Balance the book different ways in the palm of your hand. Although the force will be the same, you'll note differences in the way the book presses against your palm. This is because the area of contact is different in each case. Same, yep. Same thing, right? You're probably not going to see it on the bathroom scale, right? Will it register the book? Yeah, kind of, right? And if I go like this, is it about the same? Yeah, pretty much, right? Okay. However, the force per unit of area is called pressure. Now, this isn't actually in the curriculum, but I like talking about it because it's kind of neat. Okay? So the pressure is different. We all know that if you're out on the lake in thin ice, you need to spread yourself out. You want to have less pressure on the ice, right? More precisely, pressure is the force over the area of application, or P equals F over A. Now, we're not going to do any problems with that or anything. It's just kind of something for us to talk about a little bit because I need to explain the difference between pressure and friction. P is the pressure and A is the area against which the force acts. Force, which is measured in newtons, is different from pressure, which is measured in newtons per square meter, which is called a Pascal, named after the French mathematician Blaise Pascal. That was his name, Blaise. There's also a computer language named Pascal after him. It's a relatively new unit. It was adopted in 1960. When you hear the weather report on the TV, they talk about the air pressure being kilopascals. 101.3, I think, is standard sea level air pressure. Kilopascals. A foot-pound is a unit of a foot-pound is a unit of force as well, I think. No, a pound is a unit of force. A foot-pound. Distance, that would be work. A foot-pound would be work. Yes. Yes. Which we normally measure in joules. Okay. Many people mistakenly believe that the wider tires of drag racing vehicles produce more friction. You know the big fat tires they have on the drag cars? Not true. The larger area reduces only the pressure. The force of friction is independent of the contact area. Wide tires produce less pressure. Narrow tires produce more pressure. The wideness of the tire reduces heating and wear. Because they travel so fast and there's so much heat, when they're wide like that, they actually spread out the heat and they don't wear out as fast. How come, excuse me, this has nothing to do with what's on the page, but how come when you see the F1 cars and they're riding around on the tires, how come they don't have any grooves on them? Like, wouldn't they get better traction if they had grooves? Like, they do have rain tires, they have regular ones. Why do the tires on our vehicles that we drive around town, why do they have grooves and... Exactly. When we drive in the highways in snow and ice and rain and all sorts of things, right? The grooves actually allow the water and the snow to go into the grooves, which actually puts more rubber actually in contact with the road. The F1 cars, they generally don't race in the rain a whole lot, or they put the rain tires on. But when it's nice and dry, their rubber is flat. No No grooves at all. The grooves are only for our regular everyday so that we can get better traction in poor weather. Is it to maximize friction? They won't wear out as much, right? And they will actually. What it does is it allows the water to go away. The water actually goes in the grooves, and so it's actually dry between the rubber and the road in that brief instant. You exert more pressure against the ground when you're standing on one foot than when standing on both feet. This is because your area of contact is less. Stand on one toe like a ballerina, and the pressure is huge. The smaller the area that supports a given force, the greater is the pressure on that surface. You can calculate the pressure you exert on the ground when you're standing. One way is to moisten the bottom of your foot with water and step on a clean sheet of graph paper marked with squares. Count the number of squares contained in your footprint. Divide your weight by this area, and you have the average pressure you exert on the ground while standing still on one foot. How would this pressure compare with the pressure when you stand on 2 feet? Yes, you're going to have to read now, aren't you? Because many of you aren't listening to me. One way is to moisten the bottom of your foot with water and step on a clean sheet of paper marked with squares. Count the number of squares contained in your footprint. Divide your weight by the area, and you have the average pressure you exert on the ground while standing still on one foot. So if you stand on one foot, that must look really weird. Yeah, you like that? How will this pressure... What did she say? I probably don't want to know. Do I want to know? No, I don't want to know. I don't think I want to know. Tell me later, Hannah. So I'm standing on one foot, right? How will this pressure compare with the pressure when you stand on 2 feet? Will it be more than on 1 foot? Will it be less than when you're on 1 foot? Will it be twice as much, or will it be half as much? When you stand on 1 foot, how will this pressure compare when you stand on 2 feet? Will 2 feet be more than? Will 2 feet be less than? Will 2 feet be twice as much? Or will 2 feet be half as much? I think that's how it reads, right? I'm actually not really sure how it reads. I got to read it again, right? How will this pressure? No, you're comparing 1 foot. How will 1 foot compare to 2 feet? Will one foot be more than, less than, twice as much, or half as much? Oh, I think I read it backwards, right? We're probably going to get it all wrong. The answer is C, twice as much. 1 foot is twice as much. I probably need to rewrite that question so that it makes more sense, right? Yeah. I'll fix that. I worded it wrong, yes. Yeah, I apologize. There goes your average. I'll make it up for you. I'll make it up to you because I'm going to try this. Maybe not. A dramatic illustration of pressure is shown in figure 412. The author applies appreciable force when he breaks the cement block with the sledgehammer. Yet his friend, who was sandwiched between 2 beds of sharp nails, is unharmed. This is because much of the force is distributed over the more than 200 nails that make contact with his body. The combined surface area of this many nail points results in a tolerable pressure that does not puncture the skin. Caution, do not attempt this on your own. These are trained professionals. No, do not try it with one of your friends. Okay? I'm not accepting any responsibility. I've got it recorded that I'm telling you, do not do that. Now, there was more questions than I realized. Good thing we got the clickers. If you were to try it, and please don't, but if you were, would it be wise to begin with a few nails and then work your way up to a few more? No. Should you start with a couple nails and then try it with a few more after you get good at it? And of course the answer is no. There would be one fewer physics teacher if the demonstration performed with fewer nails because of the resulting greater pressure. You, in fact, want to start with many, 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 many more. Yeah, that would be okay too, yes. The bigger the nails would be, yeah. Now, what about the massiveness of the cement block? It plays an important role in the demonstration. So that big, it's not a cement block, it's a concrete block. My engineer friend always bugs me about that. Do you know, Jason, does your dad ever talk about the difference between cement and concrete? It's an engineer thing. No? Cement is what holds concrete together. Yeah. Concrete is cement plus gravel and sand. Cement is the powder that holds it together. It's the glue. Anyways, which one provides more safety? Which would be more safe? A less massive block, like a small, tiny block, a big, giant block, or no, I'm lying to you, and the mass of the block doesn't really matter. Oh. So what do you think? The big concrete block in the picture here, okay, what would be safer? A less massive block, a small one. If it's more mass, it would be more weight, right? So would a small one be safer? Would a big one be safer? Or does the mass of the block not really matter? It's okay to be wrong. Dana looks like it's going to be like a life sentence if she gets it wrong. And the correct answer is B. B is the correct answer. Why? Why do you want a more massive block? The greater, this goes back to that acceleration thing we've been talking about. The greater the mass of the block, the smaller the acceleration. Is the force that you hit it with going to be the same? Uh-huh. So if you got a big block, there's going to be less acceleration. So the bed of nails will be accelerated toward you at a much lower rate. Much of the force wielded by the hammer goes into moving the block and breaking it. It's important the block be massive and that it break upon impact. If you use a little tiny walnut, well, not you, the other guy. Golly gee, wouldn't it be fun to watch a video of that?